Hi friends, today we begin lecture 43 on our helicopter dynamics course, and today I am going to get the expressions for thrust and power, and finally we are going to get an expression for the figure of merit. I am Dr. Ranjan Ganguly. Now in the previous class we obtained an expression for DCT, that was a differential change of rotor thrust. So essentially if we want to get CT we have to integrate this expression from 0 to 1. And now, as I mentioned before, how simple this integral is depends on the fact that whether sigma, theta, lambda, all these are functions of r or not. Now, if we have a constant chord blade, then we can see from the expression for solidity sigma that nc by pi r is going to be constant. If we take a model, for example, momentum theory where inflow is uniform, then lambda is going to be constant. So then the key issue is going to be with theta, and if we also assume that the blade section is same throughout, then A would be constant. So let's look at a particular distribution of theta which is known as the ideal twist. So that is defined as theta equals theta t by r. Now we also presume uniform inflow and constant chord. In that case, this particular integral takes a very simple form. If you substitute theta is theta t by r, there is a cancellation and you get this integral expression once you integrate this function. So here theta t is the twist at the tip. And the reason why this form of twist is often found in books and studied is because it is a twist which leads to a uniform lambda, or the uniform induced velocity distribution around the rotor disk. And so it is a twist which we will try to get. Of course, it's mathematical in nature because at r is 0 there is a singularity, but you can get a twist which is close to the twist given here by assuming some kind of linear or polynomial distribution. So now let us turn our glance at the induced velocity predicted by momentum theory. So for climbing flight we had obtained the expression for lambda as given here, where lambda c is the induced velocity coming from the climb velocity. So it is capital V, which is the climb velocity, divided by rotation speed into radius, and lambda is root ct by 2. That's for the hover flight condition. Now typically twist varies as follows. So in most cases you are not going to get a uniform twist in a real rotor blade. So if you have a uniform twist, for example, theta would just be a constant. But what typically happens is there is some kind of linear twist distribution, and that can be written in this form here: theta 0.75 plus r minus 0.75 into theta twist. Here theta 0.75 is the pitch of the blade at 75% radius. Now this kind of twist is often used from history because of various reasons, which is essentially the fact that you look at the twist in the blade at 75% radius as a measure of the twist in the complete blade. So now let's look at the expression for CT when we have linear twist. And so what we do here is we substitute theta given by this expression here into the expression for CT, and once we perform the integrals we get this expression for CT here. So the interesting thing is, if you do this out, you will see that the term involving theta TW is going to cancel out, and you are going to only get the term involving theta 0.75 in this equation. So of course here in these integrals I'm assuming that sigma is constant, meaning chord is constant, A is constant, and also lambda is constant. That is, I have a uniform inflow model. So now let's derive some expressions for lambda. So we saw that Ct is given by this expression here for a linearly twisted blade. So if we take the expression for lambda, which is root Ct by 2, then we substitute this Ct here into this equation, we get this particular equation. Now, one of the objectives of getting this equation is that we want to find a relationship between theta 0.75 and some of the different variables. That means how much we should have for the twist. So let's take this expression and square it. We get this expression here, and we expand this out here, and then we can write this equation as a quadratic which involves lambda. Now typically values of sigma, A, theta 0.75 are known, and in that case you can calculate lambda from this equation. So that's the solution for lambda. So here we keep the root which is positive here because that's going to be physical. So this quantity which is inside the square root sign is larger than this quantity here because all these are typically positive values. So I get this expression here. So we have related lambda to theta 0.75, sigma, and A. So now one of the things you get from the relation between Ct and theta and lambda is that theta 0.75 can be expressed in terms of Ct. Now this is interesting. Of course here I am using the fact that lambda is root Ct by 2. Now what this is telling us is that one part of the theta 0.75 is coming from sigma A and Ct. So this is the mean, and the second part is the extra pitch which is needed due to the presence of the angle phi, which is essentially coming from the inflow. So now let us turn our look on power. So we start with the expression for power. Recall from the last time the incremental power dCp had a component due to the induced power, and the second component which relies on CD, that is coming from the profile power, and so we can write it in this form. Now if we do the integration, we get this expression here. Now here I have used the fact that dCt is actually this expression right here, and we have brought this here. Okay, so now if we look at this Cp, the first term is essentially the induced power loss, and essentially this is due to the in-plane component of lift. Remember that L into phi term which we had before. The second term is the profile loss, and this is where your viscous forces have started coming into picture, and viscous forces come in through CD, which is the drag coefficient of the wing section you have. So essentially this is the component which is completely missing in momentum theory, which is now captured using the BET framework. So now let's use this current theory to get the induced power CPI. So if we perform this integral lambda dCt, then we clearly get lambda Ct equals to root Ct by 2 into Ct is Ct3 by 2 by root 2. Now you will recall that this is the same expression as we obtained using momentum theory. So essentially we have obtained the momentum theory result here, and it's good to see that the BET is matching with the momentum theory result in this case. Now our condition the induced power coefficient is given by Cpi equals Ct3 by 2 by root 2. Now this induced velocity value you have seen is valid for an ideal rotor. Now this rotor is mythical, it's not real, because a real rotor is going to have realistic twist, planform, finite number of blades, and therefore the induced power is going to be greater than what is predicted by momentum theory. But again, these phenomena are difficult to model, difficult to calculate, and so on. Therefore, we need to find some way to modify this equation so that we can predict CPI better to account for the losses in a real rotor. So to do that, we add this factor, or rather we multiply CPI by this number k. And this k is an empirical factor which is obtained from experimental data by fitting the curve. So when people started getting some experimental results, they would see that there is a constant factor by which the CPI differs from what is predicted by momentum theory. And then they concluded through various graphs and experiments that k value is about 1.15, that is about a 15% excess power is required because of the presence of the losses. So now let's take a look at the profile power. So the profile power term was 0 to 1 sigma Ct by 2 r bar cube dr bar, and so when we calculate this term we get sigma Cd0 by 8. Now this is very interesting. Essentially it's telling you the profile power coefficient is solidity into drag by 8. So we can now write the total Cp, which is a much more realistic value in terms of the induced power part, which is the part involving K, and the profile power part, which is the part involving sigma. So now you can see that the blade is coming through sigma, because remember the blade is essentially the device which has CD0. It's a contributor to that profile drag or the viscous drag. And also sigma essentially brings in N, C, and R. So essentially now the number of blades and the chord are also coming in through sigma as well as R. So now we can get a better expression for the figure of merit which we discussed a few lectures before. So if you recall that definition, M was given in this manner. So here you had this part here which was Ct3 by 2 by root 2, and now we divide that by the complete power. So that's the induced power part and the profile power part. Now note that on the numerator term k is missing and the denominator term k is there, because on the numerator you are essentially using the pure power as predicted by momentum theory, which does not include any losses. So that's the induced power of a rotor which has minimum power consumption. So here this k factor is coming in, and of course this additional factor is coming in. So clearly M is going to be less than 1, because first of all k is 1.15, and then you have presence of this factor which is never going to be 0, because solidity is not going to be 0 and drag is not going to be 0 in the real world. But this equation does tells you a lot about rotor design, what you could do. Now if you look at it, you could try to make M as high as possible or as close to 1 as possible. So there are a few things you could do. You could focus on profile power, and you can focus on profile power through CD and sigma. So these two particular values, you want to have it such that M is as low as possible. And the second part is you can focus on K, which are the losses which are happening due to the various phenomena such as tip losses and so on. And if you can reduce that, then again your figure of merit would go up. So some simple solutions would be the airfoil section could be such that CD0 is minimum, so you could use wing sections which require or which create very low drag. So that's something which you can do by the airfoil design process. You could figure out ways to improve the value of sigma, and of course you could also figure out values of k or methods by which the value of k could be reduced to as close to 1 as possible. So again, these are possible approaches to design at a very high level which we can promulgate by looking at this figure of merit equation. So this equation is very important as far as helicopters are concerned, whether you are dealing with helicopters, whether you are dealing with drones, whether you are dealing with any kind of vehicle which is essentially using a rotor to take off and land. And this number gives you a good benchmark about how good your design is for the rotor and how competitive your design is with respect to different flight vehicles. So I will end this lecture 43 here. I will see you in my next video.